All right, now that we've discussed some of the components found in seawater, again, there's a lot of different things in seawater, but keep in mind the two principal components is the ones that we taste, right? The ones that we sense when we get into seawater, the saltiness, the sodium chloride. Those are the two elements that would be found in highest concentration, and those collectively make up something we call salinity, or the saltiness of the ocean basically. And table 5.3 in your book lists what we got here: four, five, six different processes that affect the salinity. And I've drawn some arrows to the left to kind of indicate like the first top four: precipitation and runoff, the melting of icebergs, the melting of sea ice. Those things would be things that would decrease salinity. You can see that's actually the next to the last column. And of course, basically the opposite, the formation of sea ice or the evaporation of water out of the ocean would actually cause the salinity to increase. Now, those may not be as obvious. The reason why salinity increases, of course, is when water evaporates or when it's formed into ice, the salt, the sodium and chloride, does not go with it. It's the water that's removed. So if, for example, you have a pool, that during the, like when it's been dry late, sometimes the way it is, you have to add more water. The water evaporates out of your pool. Well, in the ocean, the same thing happens, but again, the salt doesn't go with it. So what's left behind is the same amount of salt, if you will, with less water. So it's going to become saltier. Now, these things, precipitation, rain, runoff, and evaporation, those are all part of something we call the hydrological cycle. And there's probably nothing significantly new to you about the hydrological cycle. You've experienced it every day of your life. You've probably talked about it, back probably in grade school, right? But perhaps what you didn't know is the amount. So take a look at the different amounts. So this is what's being contributed or being removed, depending on what part of the cycle you're in. What is this, in an annual basis? So on land, that's about 96 cubic kilometers of water that comes down in the form of precipitation. So that would be 96,000 blocks, 1,000 meters long, high, and deep, right? Think of a cube. Look how much is evaporated every year, right? 380,000 cubic kilometers is evaporated every year, and it's lost through regular evaporation. That's where most of it, on the right-hand side, or through evaporation off lakes or transpiration. Transpiration is the way that water is removed from the leaves of plants. Plants also lose water. It's kind of like plants sweating. It accomplishes the same purpose in some instances. It helps the plants cool off, the leaves cool off, right? But notice how much jumps into the water dumps into the ocean from runoff. That's important, even though that's less than all the other amounts. Runoff, when it falls into the ocean or when it runs off into the ocean, brings not only the water and all that sort of stuff, but one of the things it does, of course, it brings many minerals. And that's where those the dissolved materials that you found in seawater that we looked at in the earlier table, that's where a lot of those came from, the runoff from the ocean. But I put a red arrow there to indicate that one of the problems with that too is when runoff is running off, if you will, moving to the land, oftentimes pollutants and things that aren't supposed to get into the ocean, especially in high concentrations, end up there. For example, fertilizers. We think fertilizers, that's a good thing, right? Well, it is, except when it's in excess. And when fertilizers are in excess, especially if they're used on land, like golf courses and that kind of stuff, places that are highly fertilized, the excess runs into the waters, through rain and runoff, and eventually collects in the rivers and the streams, which is a problem, but also into the ocean. And those fertilizers can cause things like algae blooms to occur, like the reason why Lake Apopka is so green. Algae blooms, you think, more algae, better, right? Well, no, because even though more algae means more food, the algae grows so quickly that they begin to actually negatively impact the other critters that, like, say, example, live in the lake or even out in the ocean. So it's all balanced, right? All right, now we'll talk a little more about this whole idea of runoff in the later chapter 11, when we discuss some of the ideas of marine pollution. But again, like I said, runoff brings the bad things. Runoff also brings the things that we naturally find in seawater, like calcium, sulfates, volcanoes. Again, these are natural processes, sulfur, chlorine. The idea behind this, though, is all of these things are going to affect the properties of water. What we might think of as the makeup of water. You have ions like the things like the chlorine and the calcium and the sulfate. Those are going to come by the river and hydrothermal vents, those kinds of things. Many times, volcanic activities will deposit ions, and there is adsorption. So the ions, when they get into the water, they do sometimes stick to things, right? Charcoal's very good at getting things to stick to it. That's why it's a filter. Precipitation is not going to remove the ions, but it's going to dilute them. And then sea spray, which would splash it up on land. Certain biological processes and hydrothermal activity, again, can remove certain ions as well, like magnesium and sulfates. Now, these are things that are part of natural processes. Again, focusing on things like river discharge or stuff being dumped into the ocean from coastal communities. If we're talking about pollutants, then we got to keep in mind that these reservoirs that we have on Earth have something called a residence time. And what I mean by reservoirs, the oceans and glaciers. Water, wherever we find water, moisture in the soil, the groundwater, and even some of the things that have nothing to do with the salt water, right, but drain into them, and also have critters living in their own right, like the lakes and the rivers, and then even in the atmosphere, there's obviously water, or there's moisture in the atmosphere. What I mean by residence time, though, look at the residence time. For example, let's look at lakes. Lakes have a 50 to 100-year residence time. Now, that's nothing compared to the ocean. The ocean's a lot bigger, somewhere in the order of, 3,000 to somewhere over 3,200 years of residence time. But think about a lake as being a sort of a confined community, which it is. If the pollutant that's in there is killing off the fish in the lake, they can't wait 50 or 100 years for it to be removed. That's what I mean by residence time. What's the average amount of time that some substance, good or bad, remains dissolved in lakes, in oceans, in rivers, all of these places? It's not just in seawater, but like I said, in seawater, since the ocean is so big, now it's not that big, especially if you think about all the rivers dumping into it. Rivers would have less of a residence time because, of course, things are flowing through it. And where things collect, like lakes and oceans eventually, or even, in some of the, like in glaciers and some of those other things that you see on there, we got to keep in mind, as I asked the question down below, that residence time and pollutants are very important. That if lakes or areas or have a very high residence time, and even though the ocean's really big, it has a very long residence time. So when we dump stuff in the ocean, like, for example, in the past, they've dumped nuclear waste, that stuff doesn't go away. For one thing, you got the half-life, and then after that, you got all that stuff that's in the water for, over 3,000 years. The ocean is not a dumping ground. It's not a bad idea. It doesn't go away just because you can't see it. Now, one of the other things that happens in the ocean, based on the stuff that's dissolved in the ocean, basically, is it changes the acidity or the alkalinity of the ocean, what we call pH. Now, I give you the formula there. I'm not real crazy about you all knowing formulas, but basically what this is telling you is that when we're measuring pH, when we're saying whether something's an acid or a base, you can see the scale on the left. Acids are things with a pH less than 7. Bases have a pH greater than 7. And you might remember that as you move away from 7, which is neutral, the strength or the acid increases. So acids become stronger as you move down the scale. Bases become stronger as you move up the scale. But all of this is tied to the concentration of something in the water. These things are hydrogen ions or protons. Again, this formula is you're basically measuring the concentration of protons. More protons means the water is going to be more acidic. fewer and very few protons means the water is going to be basic. All right, now what does this affect in terms of the ocean? Well, of course, organisms have evolved to live in many times neutral conditions, around 7, maybe a little bit on the acidic side. There are some live in very acidic conditions. The point is, critters have adapted to live in an environment that has a particular pH. And if that pH is affected and changed by things that we dump into the ocean or even by natural processes, then you can imagine we're going to have an effect on the ocean. Not only an effect on the ocean on the surface, but pH also changes with depth. All right, so this again would be something that we wouldn't necessarily affect unless we, messed with the physics of how the change occurs with depth, like you see in the picture on the right, the light blue line. At the surface, the ocean has a pH of about 8.1, so that's slightly on the alkaline or basic side. That's not bad. That's not okay. You don't have to be neutral, right? Your blood, for example, is just a little bit acidic of neutral, if I remember right. As we go down in depth, as we get deeper in the water, the pH begins to drop, okay? And we eventually get to a point where we have this kind of a minimum drop. So the pH doesn't drop much, drops down to about 7.6. So still a little bit alkaline, but becoming more neutral. The pH scale can be divided up into tenths. Now, the reason why this is, and we're not going to get into the chemistry of this, but the lower pH that occurs is because organisms are respiring. All right, so without getting into the chemistry, when you exhale carbon dioxide. And I'm going to show you a little chart here in the next slide. Well, you know what? Let me go to that one now, and then I'll come back to this one, and we can finish up what happens. But let me talk about this animal respiration thing. Again, without really getting too much into the chemistry or how this happens. But carbon dioxide from the air and carbon dioxide from organisms that live there mixes with the water that's in the ocean. It makes something called carbonic acid. All right. Now that changes the pH of the water. Again, don't bother looking too far to the right. Again, it's all about hydrogen ions. But what we got here is a buffering system. It's important to keep the ocean. It's important to keep your body at a particular level, right? It's that balance, homeostasis, and that involves also pH. So even though your blood is, 6.8, it's good that it stayed just about right there. You don't want it to fluctuate a lot. You don't want it to be out of balance. Now, the same thing's in the ocean. So the carbon dioxide that the ocean absorbs from the air, there's a lot of carbon dioxide out there, affects the pH because it's turned into this thing called carbonic acid. And acid's going to affect pH because, right, that's what acids do. So down below, if you really want to get into the details of what happens, I've showed you what happens if the ocean is out of balance, if it's too basic or too acidic. But again, this idea, don't worry about that. It's the hydrogen ions that are changing all of this, right? So the hydrogen ions are changing what the pH is. So that happens by they absorb carbon dioxide. We exhale carbon dioxide. So back to that original one. So we're actually causing the pH to drop. Now, I know this seems a little confusing because you said it's getting more something. It's getting more acidic. It's becoming less basic. The pH number is dropping. And then it begins to rise again, and the pH gradually increases, and then eventually it levels off, right? Levels off at a particular depth. This is interesting, this curve, because this curve we see in some form or another, this kind of dropping and then sort of leveling off, is one that we see in other oceanic conditions, other properties of the ocean. And I'll get to that in a second, all right? So, again, takeaway here. Hydrogen ions are what causes the pH in something, and in the ocean, the carbon dioxide from the air, as well as the carbon dioxide from organisms respiring, affects the pH. It literally tends to make it more acidic. Oh, look at this. This is kind of neat. I like this. Sometimes it's really good to put two graphics together. And here we got salinity and temperature. And then the ocean is kind of nice, or the map behind is kind of nice to show us where. So we're moving through latitude on the y-axis. So we're going from the North Pole to the South Pole through the equator in the middle. Let's look at temperature first. That's one that kind of makes sense, right? It's colder at the poles. Average temperature is warmer at the equator. Yeah, no kidding, right? Now look down below. Look at the salinity though. Notice the salinity has something that we call a bimodal distribution. Bimodal. I don't. My pen is not working, so I'm trying to spell this with my mouse, and I'm left-handed, and my mouse for some reason I've always used on my right hand. So bimodal. Two modes. A mode in statistics is the number that happens a lot, the most frequent number. So when we look at salinity, we find that there are two peaks, so it's bimodal. So salinity peaks at the Tropic of Cancer, which is 22.5 degrees. The Tropic of Capricorn down in the southern hemisphere, it peaks again, 22.5 degrees. That's the tilt of the Earth, or about 23 degrees. That's why it does that. That's why we call those things the way they are. It's the furthest distance that the sun appears, because it's really the Earth tilted that causes it to do that. Remember from earlier chapters, the sun appears on the horizon, 22 degrees north, about 23 degrees actually north and south. So you would think, though, let's jump to the equator for a second. You would think at the equator the salinity would be the highest, wouldn't you, right? Because the temperature is the highest. Remember, evaporation takes away the water, leaves behind the salt. But the salinity, remember, ecosystems or parts of the Earth are in a balance. So even though there's a lot more sun at the equator, on average, the equator receives more sunlight, so you think would be warmer. Temperature graph shows us that. There's more of evaporation, yes, but there's also more rain. See, it's balanced together. At the mid-latitudes, at the lower latitudes, the salinity is going to be lower. It's warm, there's high evaporation, but there's a lot of rain, and rain tends to ride the evaporation, so salinity drops. Salinity is going to be lower, at the poles, at what we call the higher latitudes, right? Because a lot of sea ice is melting, so a lot of precipitation, a lot of runoff. Now that rises going towards the Tropic of Capricorn and Cancer, because right there we got the Goldilocks routine, right? At the mid latitudes, the salinity is going to be higher, because what you now have is you got dry air, and you're going to have a very high evaporation rate. So you get the warmth, not as much as the equator, but you don't get the rain as much. If you've ever studied geography in school, you know that that's why when we look at the deserts on Earth, most of the deserts on Earth occur at mid-latitudes. You know, like the desert southwest United States and the deserts. So these are tropical, right? Lots of rain, lots of heat. This is tropical up for our end of it. The equator is somewhere in between there. Okay? A bimodal distribution in salinity, while temperature then would just be modal, unimodal. Temperature peaks only in one place. So it all balances together. It's kind of cool when we look at that, especially in human beings, right? We're visual creatures. So this is really kind of neat, because this is the Aquarius satellite taking a picture of the ocean temperature. I'm sorry, not the ocean salinity. The red being higher salinity, and the blues and the purples being lower salinity. I said temperature because, of course, if you look at that, you might think, okay, yeah, I see what he's talking about. It's going to be warm in those mid-latitudes. Notice that right along the equator, though, the salinity drops, doesn't it? It's a little, excuse me, it's a little more. It's a little less obvious, that drop along the equator in the Atlantic. Hold on, I'll tell you why that is in just a second. But in the Pacific, it's really obvious how along the equator the salinity drops. A lot of rain, right? A lot of rain, a lot of heat. The reason why you see such a dramatic salinity in the North Atlantic and the South Atlantic. In other words, why it's so extreme there, it's the same reason why it's extreme in the Med and in this area here, confined areas. The Atlantic is smaller than the Pacific, north and south. So you got a larger area of the water to heat up, so you're going to affect the salinity again. See, it's all tied together. So my goal, when you're looking at a chart like this with you guys, is to be graphically literate, to make that jump and go, oh, this is salinity. Why is it the way it is? Oh, yeah, that's right. Because at the mid latitudes, where you see the brighter colors, you get that warm air, but it's dry, so you get a lot of evaporation. Why wouldn't it be higher at the equator? I would expect with a higher temperature, but there's also a lot of rain. Okay, and then the sea ice for the poles. Isn't that neat? Okay, the curve I was just talking about, the one that happens with depth that we looked at with pH, also happens with salinity. All right. So across the top chart here, we have salinities from 33 to 37. If you want to make read that as percentages, 3.3 to 3.7% salt. We measure salinity a little bit different. We call it, remember, in parts per thousand, but that's about it's not about it is 3.3 to 3.7% salt. That's at the surface, and as we get in depth, that salinity changes. For example, if you're at the higher latitudes, all right, so you're up around the poles, a lot of precipitation, a lot of runoff, the salinity is going to be lower. It increases as we move through an area on the right that I'm pointing out called the halocline. Now, it increases because of changes in chemistry that occur. A cline, you're going to see more of the one in the next slide here in just a second, is a change, a very distinct change that occurs. So in this particular case, we have a halocline. Halo is salt, salinity. So this is a change in salinity. At the higher latitudes, it increases. At the lower latitudes, it decreases. Remember, at the lower latitudes, the salinity is going to be higher. But now, and we're not talking about the equator here. We're talking about those ones. I guess that should be actually reworded a little bit better. We're not talking about the lower latitudes in terms of the equator. We're actually talking about those mid latitudes. You're going to have a much higher evaporation rate. All right, as in those areas. Yeah, that's the way this graph should be read. Sorry, I confused myself there for a second. So low latitudes really, I need to change that in my chart. Let me go back for a second. So the lower latitudes, in this case, we were talking about the equator. Here, that should really say mid-latitudes. Mid-latitudes. Mid-latitudes have higher salinity because they have higher evaporation, less precipitation. The tropics would fit somewhere in between, actually, because of the rain. Anyway, so we get the halocline, right, this change that occurs. And then down below, things can become relatively constant. That's not just in salinity either. It happens a lot of other things, too, like temperature, for example, which we'll look at in just a second, and density, okay? But halocline, so that the salinity starts off higher in the mid-latitudes, drops, the salinity starts off lower in the higher latitudes, and then both of those change through the climb, but they gather. And again, what this means, folks, is stratification. So from a biologist point of view, you're looking at this going, oh, I bet you there are different critters living in different areas. Critters that live on the surface, critters that can live in that area where things are changing and can change, because these curves can move up and down, right? The curves can, the change that occurs in salinity in this case can change depending on, say, for example, in a local area where maybe there was a lot of rain lately and that kind of stuff, okay? All right, keeping up with the curves, look at temperature on the left-hand side. Look at that. At the higher latitudes, all right, at the higher latitudes, so now we're talking about the poles again, it's cold. Okay, and it's cold from top to bottom. All right, so that's easy enough to remember. It's cold it's not balmy at the top of the water up in the poles. It's cold or down at the poles. It's cold and cold all the way to the bottom, so you don't get a lot of stratification. So organisms in the poles that live there are probably not going to live at a different depth because of temperature. It might be something else, but it's not going to be temperature. But in the lower latitudes, all right, in the lower latitudes where you're going to have this warm temperature at the surface, right, and it's going to get colder, and it's going to go through now this time a thermocline. It's going to drop. Now there's specific definitions for clines, like the temperature has to drop, if I remember, in a thermocline at least 1 degree Celsius for every meter in depth or something like that. Or it's not quite that, I don't think. But anyway, don't worry about that. A cline, it's a temperature change, right? It's getting cooler, it's getting cooler, it's getting cooler. Organisms that live there are going to have to deal with that because that can move up and down with the seasons, right? It could stay warmer. It could be warmer deeper during the summer, less warm during the winter. But then again, it levels off where it becomes cold again, uniformly cold. We don't care where you live at the poles or at the equator. When you get down below about 1,000 meters, it's cold all the way to the bottom. All right. So again, this is going to cause the ocean to layer. So we have a surface layer of, about 200 meters or so, an intermediate layer, and these things change, and then a deep water layer. The surface layer is going to be a layer that's mixed. What I mean by that is because of the changes in temperature with the seasons, right? The water at the top gets warmer and cooler and gets more and less dense. Cooler water is heavier. That's why it's at the bottom of your pool or bottom of a pool. So during the winter, that cool water at the top is going to get heavier and begin to mix and fall below the water below, which is warmer, right? So this is going to cause mixing to occur throughout the seasons. That's above the thermocline. At the thermocline, we get the change, and then down below, there's no mixing. So again, these kinds of things are going to affect organisms. One of the things that early oceanographers noticed was that stratification occurred in the ocean. There were things that lived at the top, things that lived, intermediate, and things that lived down below. All right, and that's going to affect, obviously, the way they survive, their survival techniques. Now, the one on the right is showing you the pycnocline. I think, isn't that spelled wrong? I thought it was a pinocline. Let me double check that for a second before I, might not be a pinocline. I got that wrong. Those words are sometimes no, that's right. Pycnocline. All right, pycnocline. Pycnocline is density. And I thought that word was, I guess that is spelled right. Every time I look at that word, I'm always thinking there's a C in the wrong place. That's an oddly spelled word. But many times in science, when we're trying to pronounce words, it tends to be very phonetic. So you might want to say pycnocline, but go with the other way you can say an I. So pycnocline. Pycnocline is changes in density. All right, so we got halocline, changes in salt, thermocline, change in temperature, pycnocline, change in density, right? So in this case, the pycnocline is opposite of the thermocline, right? The thermocline that we saw there, at the top it's higher, it drops, okay? And the pycnocline, what we have at lower latitudes, right? So what we have at places that are at the poles where it's very close, the density is lower and it increases as we drop. At the higher latitudes, though, we're, again, really talking about those mid-latitudes, the pycnocline, well, the pycnocline doesn't exist. A cline, there's no cline, there's no change. The density stays about the same from the top to the bottom. Okay, now, density is dependent on a couple of things in water. Dependent on many things, but the things we're going to worry about is dependent on temperature. All right, and it's also dependent upon salinity. So up at the lower latitudes, the density is going to be higher. Or I'm sorry, excuse me, it's going to be lower. Up at the poles, the density is going to be lower. See, sometimes even when I think about these things, I have to really concentrate on what I'm saying because I get it backwards. Okay, I have to think to myself, why is the density be lower up around the poles? Lots of ice is melting, lots of precipitation, lots of stuff dumping into the ocean. So there's going to be less salt. It's going to be diluted, so the density is going to be lower. More salt makes water more dense. Yeah. When you dissolve things in water, it makes the water more dense. Temperature does too. It's not that I'm discounting that, but I'm talking about just the salt right now. So now what happens, though, is that we get this pycnocline. And density is inversely related to temperature. So the deeper you get, the colder or the water gets, obviously, and the greater the density becomes. See? So the density is inversely related to temperature. And the deeper you get, the colder you get. All right, so notice, once again, through the pycnocline, the density is increasing. Now, when you get down below 1,000, 1,500 meters, it's cold. It's dark. There's a lot of pressure. It's cold. Look at the thermocline. You're down somewhere where it was, even if you're at the equator or in the mid-latitudes, you're down where it is around the poles. It's cold. It's less than 4 degrees Celsius. That's cold. Water freezes at a 0. But, you know, you would think, okay, well, what's happening to the density, or what's happening to the salinity? Well, the salinity is mixing through the water and doing its thing. But that's going to be overcome by the temperature change that occurs at that depth of about 1,500 degrees, where it starts really getting cold and uniformly cold. So it stays pretty much the same all the way down to the bottom. Pretty much what you would find in the higher latitudes. So there's temperature varies with depth. Density varies with depth, pH varies with depth, salinity varies with depth, and they're all tied into one another, right? The pycnocline is tied into density, which is tied into salinity, right? The temperature is tied into depth. And all of those things balancing together is going to cause different stratifications of salt, of pH, of temperature, and of density related to salt. Many times, right? But then you have to keep in mind that it's not just salt with density, it's also the temperature. It's this delicate balance that occurs. All right, so that's it for chapter 5. Let me stop the recording.